Hey, yeah, my name is Joe. I'm a postdoc here at Columbia and Leap, and I'm just going to be talking about some things that are going on in the ICE Microphysics project. So it's going to be kind of a little bit of this and that, a potpourri, just an overview of what's going on in this world, specifically some challenges of ICE Microphysics, some progress, updates, and some current and future opportunities. And also just want to acknowledge this whole list of collaborators that this work wouldn't be possible without. So, and just wanted to, I just found this animation of like someone made clouds in Minecraft, and I thought this was like really apt kind of metaphor for how like a climate model might see clouds. So I just thought that was funny. But yeah. So just to outline, I'll just give a brief background for why this is important, why ice clouds are important, and specifically in the context of climate models, and then talk about some two specific projects that are more in the mature phase, where we have a roadmap for implementation in NCAR's CAM. First will be this work led by Kara Lamb, where she used neural ordinary differential equations paired with lab data to learn a functional form for ice crystal growth. And second is some work that I've been leading using in situ measurements and machine learning to improve some functional relationships between mass and size for ice crystals. And number three, I'll just talk about some exciting things that we're thinking about in terms of incorporating some latest advances in representation learning and some collaborations we have with computer scientists, and also how we can leverage high fidelity simulations, in other words, cloud scale large eddy simulations. And then I'll wrap up and we can crawl our way to lunch. So just to give some background, so why are clouds important is essentially they exert a strong influence on Earth's energy balance and also water cycle. Ice clouds in particular are poorly understood, so I'll just read this quote from the IPCC report. The role of thin cirrus clouds for cloud feedback is not known and remains a source of possible systematic bias. The representation of cirrus in climate models appear to be poor, and such clouds are microphysically complex. So and a large part of that is due to just the sheer number of processes that we have to represent within the grid box of a climate model, right? And this on the left is showing a visual representation of that, and on the right is a spaghetti plot of all the various states of hydrometeors that have to be represented and how they change over time as the model steps and chugs numerically, right? So, and specifically for ice clouds, these are the states and processes that have to be represented. So this comes as no surprise to anyone here, but here at LEAP and also for ice microphysics, this is what we're trying to do, incorporate the various facets of what we know from physics, from observations, and also machine learning to improve these representations of these ice processes. And I think this first example is just a great representation of that, the synergy between those three facets. And when I say we in this next section, I mean, I specifically mean Carol Lamb because she actually did the foundational work for this, and I'm just going to carry the torch to implementation for this. So just to give you a brief overview of what this project entails. So say we have a ordinary differential equation, just some functional form of mass growth, dm dt, as a function of various variables and also parameters. And for example, we have this deposition coefficient alpha, which in literature, there's a lot of contention about. There's various values that have been put out, and some people um, often assumed to be constant, but some people say like maybe this shouldn't be constant. So what if we can use lab data where we can actually measure the growth of single crystals to inform this growth rate? That's exactly what Kara did using this framework called neural ordinary differential equations. And this is kind of the setup for the data that we have. We have 290 single particle growth experiments. And these experiments were done by Jerry Harrington in his lab at Penn State. So these crystals are grown at different saturation and temperatures. And on the right is a time series of mass growth for each of those 290 crystals. And what Kara did is essentially fit either different parts of this mass growth rate with the neural network using this framework called the neural ordinary differential equation, which incorporates whatever traditional time integration scheme you want, for example, Runge-Kutta, and essentially using stochastic gradient descent, you're minimizing the distance between the observations, which are from the lab measurements and the model. And the cool thing that Kara did in addition was essentially find a functional form for this neural network learned function so that we can plug this into a climate model without some kind of Python to Fortran bridge. And this is a lot going on here, but just the bottom line is that the weakly constrained node model performed the best, had the lowest mean squared error, and had the best fit for 154 out of 290 experiments. So we thought, and as I explained, she used symbolic regression to learn a functional form that can directly be implemented. You just code up the math, right? We don't need any bridge. So this is the part that we're going to be working on with NCAR collaborators Hugh Morrison and Trudy Eidhammer in the spring. So we can do some preliminary tests with single column CAM and run some sensitivity tests. So that was an overview of this node work led by Kara. Now I'll shift into some of this work with that I've been doing with in situ optical imagery and synthetic data, where we want to constrain some relationships between mass and size, which are important for microphysics. So the context of this is that shape of ice matters. Shape is generally thought to be a function of its environmental history, and the shape influences the process, and vice versa. It's a two-way street, right? And just to illustrate, in this study by Jarvin et al. In 2018, she found that ice complexity may induce additional cooling sensitivity of about 1 watts per meter squared. And for reference, CO2 radiative forcing is about 2 watts per meter squared. So this sensitivity to shape and ice complexity is not negligible. So our current understanding of ice habit or ice shape is mainly driven by optical imagery, which optical imagery probes, which are mounted to planes and they fly through, real world clouds, and we get an idea of what these crystals look like. And on the right, for example, this is some past work where they use supervised machine learning to classify these ice crystals by some predetermined classes of of expert-driven shapes. But what we really want to know for parameterization is this relationship between mass and size. But from an image, it's really hard to predict for complex shapes, the mass, or other 3D relevant properties that you might be interested in, like surface area. So we thought, why don't we just do this or come up with a framework to do this with machine learning? But the problem is there's no ground truth because these optical imaging probes, you can't measure the mass in situ, right? So what I did was develop synthetic data from some prior understanding of what these crystals look like. And what I started with bullet rosettes, which are these spiky looking crystals here, because they constitute about 50% or more of the crystals in high cirrus clouds. So you can computationally generate random variations of these, like thousands, millions of these, and then you can train a machine learning model on these synthetic data and hopefully transfer this to the real CPI data. So that's exactly what I did. This is kind of what this framework looks like. You generate a bunch of synthetic data, you take snapshots of this data, you know the ground truth of the properties that you want to predict, like mass, surface area, the number of spikes, and you can either directly use the images as input using something like a convolutional neural network, or you can do feature extraction and use more traditional ML methods like random forest or even linear regression, right? So just to illustrate that this works for surface area and mass, respectively on the left and right, we had some pretty good performance. And of course, you can do this with a convolutional neural network, so you can circumvent this feature engineering step. And what working to wrap this up, and I'm writing a paper on this right now. And of course, our end goal is to revisit these mass size relationships with millions of CPI images so that, and we're going to compare to the existing lookup tables that exist in the NCAR CAM model and update as necessary. So that's kind of the roadmap for where we're heading towards the end of this year. How much time? Oh, good on time. So Next, I'm just going to be talking about some ongoing work and just some more experimental things that we're trying. So this first project that I'm going to talk about is about representation learning for a distributional understanding of ice crystal habit, and I'll explain what that means. So just going back to this for context, as I explained, some people have used supervised classification to basically classify ice crystals by habit, but this relies on some assumptions that the ice, for example, has hard classes. But we know if you look closely at the ice crystal imagery, there's a lot of ambiguous crystals. And in addition to that, the process of hand labeling is very laborious, right? So what we thought about was potentially using representation learning. And I'll just read this definition by Joshua Bengio, who is one of the forefathers of modern AI. So representation learning is defined as learning representations of the data that make it easier to extract useful information when building classifiers or other predictors. Very, very broad, but essentially learning the essential features of the data, right? And this can be in terms of learning the essential features of the state. And as I'll mention later too, you can also do this to dynamics, learning processes as well. So this is a collaboration that we started with some computer science researchers at Linköping University in Sweden. So Kara and I met them when we were over there in October for this ML and climate science visiting scholar period, and they saw some of our work and were interested in collaborating because they developed this self-supervised method called Dino VMF. And for more details, you can look at this paper, ICLR paper. But essentially, it's a state-of-the-art representation learning model based on vision transformers, and they predict a soft distribution over k components on a hypersphere. So we thought, why don't we try this on the CPI data? So we did a prototype of this. Hari trained this model with about 20,000 training samples. And what you're looking at is these 69 clusters, where the top row is some random samples that are closest to the centroid of the cluster, and the bottom row is crystals that are further away from the centroid. And the distribution that you're seeing on the bottom is a similarity distribution, where right-skewed distributions are more homogeneous clusters, and more normal or left-skewed distributions are more heterogeneous. So this gives us a framework to look at ice habit from a more data-driven perspective and not without any prior bias about what these crystals should be classified as. And just to do some verification, we can train some linear classifiers based on these extracted embeddings from the transformer to see like if they can predict these classes. And as a first pass, we see that they're actually doing pretty well at learning representations compared to the state of the art on the right, where they use a fully supervised approach. And we don't expect this to perform as well as the supervised approach because the goal is not to do the supervised classification. This is just more of verification that the model is learning some representation that is meaningful. And the end goal is this is that we want to update existing habit diagrams with soft distributions of learned habit representations. And what I mean by that, this is a canonical habit diagram from Bailey and Hallett 2009, where they show essentially these discretized in the space of like humidity and temperature, where these different shape categories exist, but they're like hardly categorized. So we're thinking we can use these high dimensional latent embeddings and learn soft distributions to replace this kind of traditional habit diagram. And this is something we're actively thinking about. See, a little bit more time. So next, I'll talk about how we can use high fidelity models or large eddy simulations to reduce parametric and structural uncertainties. And this is some work that we've already started, but we want to go further with this. So we've already run some ensembles of large eddy simulations of cirrus clouds shown here on the left. And oh, maybe I should back up a step and explain what the difference is between the left and the right. So the dynamical model is the same, the large eddy simulation, but the microphysical representation is different. So on the left is a bulk LES, where in each grid cell of the large eddy simulation, you're representing the distribution of ice crystals by a prescribed distribution. On the right, we don't have a priori shape of the distribution. We're tracking individual particles that are representative, and we're explicitly advecting that through um, the simulation domain. And that's called a Lagrangian superdroplet model LES. And this is the state of the art, best we can do in terms of modeling cloud microphysics. So one thing you can do, for example, is to study like how different is the bulk from the Lagrangian and what happens if you perturb different parameters, right? And that goes to probing structural differences and also parametric differences. And what I mean by that is structural refers to the differences in like the framework, for example, bulk versus Lagrangian, and also the differences in the mathematical representation of those process parameterizations. And on the right, it's for parametric, I'm referring to those coefficients that we typically assume to be constant, that are empirical or theoretically driven. So how do we address these two forms of uncertainty? So on the right for parametric, this is work that a lot of people in LEAP are already doing with different parts of the Earth system model. For example, Kate with warm rain or Linnea with land modeling. You can do ML-assisted perturbed parameter ensembles and estimate some posteriors for those parameters. And specifically for our simulations, where we don't see overlap between the high fidelity model and the bulk model, we're thinking about using something like approximate Bayesian computation, which doesn't basically don't need likelihoods, so you can do this estimation without any overlap in the model metric output. And for the structural, what we're interested in is kind of carrying on what Kara already tried with warm rain microphysics, is essentially doing this reduced order modeling, which is another form of representation learning. But in this case, we're learning an ideal process representation for microphysics, essentially taking that Lagrangian superdroplet model and try to retain the fidelity of that, but make it computationally tractable in a condensed form. And that's something that we want to try with ice microphysics. And of course, all of this is within the framework of observations, which we need to constrain top down, because without some form of ground truth, we don't know in which direction we're going, right? So that's always something we have on the back of our mind as well. And we have some ground-based radar for these simulations that we're simulating, which is a specific field campaign called IceBall. So with that, I will conclude. So I showed you an example of Kara's work where she applied neural ordinary differential equations to lab measurements to develop a physics-informed machine learning parameterization for ice crystal growth. Second, I presented my framework for predicting 3D relevant properties from 2D images using supervised machine learning and synthetic data. And finally, we think there's a lot of promise in representation learning, and I don't pretend to be an expert in this. I'm relying on the expertise of a lot of collaborators, but we think there's a lot of promise for this in learning both state and dynamic representations for ice microphysics. So with that, I will conclude. Thank everyone who's helped me along the way, and yeah, that's it. Thank you.
Hi, Joe. Thank you. Outstanding work and talk. I guess a question. Well, I have a question, perhaps two, on the representation learning. And I know you anticipated that maybe you're not the expert, but I thought it was really cool. And I was wondering if you could say a few more words about how the training process happens for the transformer and whether the clustering is part of the process or if you basically use the representation that you have learned as sort of your metric or similarity metric for the clustering.
Yeah. So to the extent of my knowledge, the clustering is not done post hoc. It's done with the training. So those are actually the backbone embeddings from the transformer. Yeah.
How do you determine if two ice crystals are similar? I guess it's my
Yeah, I guess then that goes back to like validating that some robust representations are being learned, and that was kind of what I tried to show with the linear classifier. Yeah.
So I noted in the first two parts, your the result ends up that you don't need to implement machine learning in the Earth system model, which is, we know that that's good, either because you don't have to code it up in Fortran or you don't have to build a bridge, right? But I wonder, was that like that just happened naturally out of the process, or was that like part of the plan? And then if it was part of the plan, what were there compromises you had to make in order to get to that point, in order to achieve the applicability to the ESM?
Yeah, I think, well, at least for Kara's node work, that was definitely part of the plan because I know that was like always a hurdle for implementation. And just to like show, uh, sorry to do this, but basically this shows that the node or the symbolic regression functional form is pretty much equivalent to the neural network form. And that's to maybe answer your second question. And then for the mass size relationships, we haven't really, I guess you could go like a neural network route or something, but I think we're just going to go the lookup table route um, just because of efficiency. But that's something to discuss with like Hugh Morrison or someone who's, an expert at NCAR. Yeah.
We have a question online. Thanks for the great presentation, Joe. Yang is wondering, what is a soft distribution?
Yeah. So in a nutshell, it's like basically not assigning to a single class, is assigning a probability um, that, a particle might belong to a certain class. Probabilistic instead of hard classes.
Thanks for a great talk, Joe. I'm wondering, like, when you're talking about the implementing the mass diameter relationships, would you like add some degree of stochasticity, or would you make it deterministic? Have you thought about that at all?
Yeah, Kara and I have been talking about that, and we want to try experiment with some stochastic parameterizations. Yeah, if you have any ideas, we would love to hear. Because there's a huge spread. Yeah.
Hey, we have a question from Marcus. Are those soft probabilities represented in your comparison of your classification to the labeled one?
No, not for that figure that I showed. Yeah.
This is Tian. I'm just gonna unmute and ask my question. I think my question is on one of your slides. You said there's no combination, like the first part, the labeled classification and the supervised classification, and the Van Mises-Fisher mixture model. That you said this two, like one is unsupervised clustering, the other is labeled. I think there's a natural way of combining the two, because you have valuable labeled data that can drastically improve the learning of the embedding through like metric learning and stuff. So I think there is a natural way of combining the two.
Yeah, that's a good point. We have also discussed that with our collaborators, like semi-supervised methods. But I just want to make a comment that one drawback of using labels is that we don't know if the labels are accurate in the first place. So we want to circumvent labeling.
Right. So my suggestion is, so I think the keywords is not supervised, it's not semi-supervised learning that you should look for. You should look for metric learning. You should also look for weakly informed learning, because the weakly supervised learning allow the label to have mistakes. You can actually make assumption about what the error could come in. And also I think there is possibly a natural reason why the Van Mises-Fisher model works, because I use the Van Mises-Fisher embedding for social science research. The nice thing about that embedding is that it doesn't have a boundary, which a lot of the natural system it is in a constrained space. It's a sphere rather than it's a plane. So it just naturally have some physical properties that may be attractive for leap study.
Got it. Thank you for that comment. Yeah.
I think we're all set. Thank you so much, Joe.